So welcome everyone. This is our April 2022 Science on Tap. Um, so this event is held by the Science Policy Society at Penn State, and we are a group of mostly graduate students in different areas of science who are interested in interfacing with the roles that we can play with policy making. So one important pillar of our organization is science communication. And one way we facilitate that is through this outreach event called Science on Tap, where we bring in researchers to discuss the science that they do in a way that is accessible to the general public. This event is usually a big hit, and we're excited to have our three speakers here today. Sierra, do you want to go ahead and introduce them?
Sure, yeah. I know Lauren is going to explain GradWIE in a little bit more detail. Graduate Women in Engineering, GradWIE is kind of for short. But I am happy to introduce Lauren, Dennis, Harula, Zamaris, and Gabby Salai today, who are three graduate students in the College of Engineering who are going to talk about the research a little bit, but they're all amazing. Lauren is the president of Graduate Women in Engineering for the past year and has done amazing work. Harula has been the vice president. And Gabby the treasurer, and both are amazing as well. So we're really excited today for them to be able to share their work with you, and thanks for coming.
Awesome. Thank you, Sierra. I just want to shout out Sierra for putting so many wonderful opportunities for members of GradWIE together. And we'll go ahead and get started. I'll go ahead. Oh no. This always happens. The bar is in the place. Okay. So briefly, I'll just touch on, actually, can you see?
We can see presenter mode.
This happens to me every time. I just learned about the two-screen life. So pardon while I'm getting like caught up to the 21st century. Anyways, so Graduate Women in Engineering is an organization that we started about a year ago, and it really came out of a program in the College of Engineering led by Cindy Reed, a Graduate Women in Engineering program. And we won't dwell on this too much, but we just wanted to sort of advertise our organization for those who are interested, and also sort of describe the values of GradWIE, because I think it links well to all of our research interests. So the purpose of GradWIE is to create an inclusive community to support the success of graduate engineering students. And we explore and highlight the engineering experience through the lens of gender, but we don't exclude any other lenses or foci or experiences. And so we really aim to create a community of support that supports both professional well-being, but also just well-being generally. So this includes like peer support, creation of safe spaces, hosting social events, providing diverse resources, and also professional development. And so all of this is sort of in response to a desire from all of the members to want to create a space for well-being through the College of Engineering and also for graduate students. And I think a lot of our research also reflects our interest and desire for this. And so I'll go ahead and get started. My name is Lauren. I am a PhD student in civil engineering, and I also am getting a dual title in climate science. So I work with Caitlin Grady, who's also a professor in civil engineering, and she also has an appointment in the Ethics Institute. And so today I'm going to talk about infrastructure related to energy and hydropower and climate risks, but I'm particularly interested in infrastructure sort of from an ethical perspective. And so infrastructure, I think in this day and age, is really a means through which we satisfy some of our most basic needs. So this is one of my favorite figures from a paper from two scholars called Clark and Seeger. And they sort of link infrastructure, like on the left-hand side here, you see emergency services and public health and water at the bottom. And you really sort of realize your basic human needs like air and food and water through the vehicle of infrastructure. And so in today's modern world, infrastructure is super important and is also increasingly complex, especially energy infrastructure. If you think about all the different infrastructure that depends on energy infrastructure, this is really sort of a basis for how we meet a lot of our needs. So this sort of like frames our work and our interest from a sort of ethical standpoint. We want folks to have access to infrastructure, and we want that infrastructure to be resilient. And so in a changing climate and in a world where we want to both have human health and environmental health, we're transitioning to renewable energy. And this is happening all over the US. So this chart that I borrowed here shows the share of electricity generation that comes from renewable energy. And they're counting like biomass burning and all sorts of sources. But you can see it's really happening like all over the US. And a lot of these sources are variable. So like sun doesn't always shine, the wind doesn't always blow, as everyone in this room knows. And so there are challenges with incorporating some of these variable resources into the grid. And so that's where I think hydropower plays a really interesting role. So hydropower, although it only makes up like 6.7% of the electricity generation in the US, it can be used in a lot of different ways to support renewables that are variable. So for one example of this is that because hydropower is a sort of stable source of energy, so the water flows downhill through turbines and creates energy. As long as there's that water source, as long as the river is flowing or the reservoir is full, you're able to consistently generate energy. And so it can help manage sort of flexibility within the grid or frequency regulation. Hydropower is also super important because of its capability to act like a battery. So for example, when you have lots of solar energy in the middle of the day when the sun is shining so bright, you have so much extra energy, you can use that energy to pump water uphill into a reservoir and then let that water down later when maybe the sun is down and there's less solar energy. So this really is like the oldest form of a battery that we have on the grid. And as we try and incorporate more renewable energy, hydropower could play a really important role. But due to climate change, hydropower is going to face some changes in the future related to water availability and the timing of the availability of that water. So let's say you have a stream, the temperature is increasing. There are multiple sort of things that could happen with increasing temperature and stream flow. So first, the increasing temperatures could cause a bunch of evaporation and you could have less stream flow or you could have drought. But sometimes increasing temperatures can also cause more precipitation because the water can hold more air or more water when it's warmer. So there are all sorts of variable impacts that could occur, and it would depend on management factors and geography and all of this complexity. Changes in the timing of stream flow could also be really important. So say that their precipitation falls as snow and that snowpack slowly melts, and now you don't have that snowpack anymore and that precipitation is falling as rain. That could really influence how the timing of the hydropower that you receive is going to come in the future, essentially. So on a global level, some studies have suggested that hydropower overall potential will decrease. And there are some examples of some of this actually happening right now. So Lake Oroville, for the first time, had to shut down their hydro plant last August. So this is not only sort of projected changes, but some of these changes are being felt now. And the people that are going to have to, so first, I guess I'll just show you that these changes vary geographically. So for example, if you look on the west coast of the US, some of the main drivers of changes to hydropower include like earlier snowmelt and drought and decreases in stream flow, whereas in the East Coast, you're going to have more extreme precip and you might have flooding. So this really depends on where you are. And the folks that are going to have to respond to some of these changes are called balancing authorities. So balancing authorities are basically like the air traffic controllers of the grid, right? They like send electricity where it needs to go at the right time, and they balance the supply and demand of electricity. And so they are really going to have to sort of deal with some of the changes in generation from resources that are impacted by climate change. And so one of the ways that we're thinking about studying sort of these changes in the natural system and how the entities, the institutions that are going to have to deal with this are through networks. So a watershed is like the entire land area that can contribute to a stream or a water body. And so we're thinking about this in the scale of watersheds, the land area that contributes to, for example, a reservoir, and the balancing authority. And so changes in a watershed can affect how much electricity a balancing authority receives and how much they could send to other balancing authorities. So we're thinking about this through a network system. So for example, these little icons with the streams, we connect them to one another if water flows from one to another, one landmass to another, and balancing authorities are connected if they exchange electricity. So in this way, we can kind of look at and analyze how risk could travel through the system, how natural impacts could affect the physical system. So our real question is, how hydropower assets within each balancing authority will be affected by climate change? Because realistically, that's going to impact, folks who are receiving electricity. So like I mentioned, we're doing this through a networks approach. We have a top layer network that is comprised of watersheds. And so this is where we'll assess the climate impacts. Again, they're connected to one another if water flows from one to another. And then we also have nodes in our network that are balancing authorities, and they're connected to one another if they can send electricity to one another. And then these two networks interact if, for example, a balancing authority has a hydropower facility in a particular watershed. So like, let's say a drought occurs in the top left corner. That drought could travel to other watersheds, or it could impact a balancing authority, and then that could impact other balancing authorities if they normally transfer electricity to one another. So by creating this network, we found some sort of interesting conclusions. So if you remember, I think it was a couple years ago in Texas, they had a really bad winter storm that really was not good. And so one of the reasons it was so bad is because their balancing authority, ERCOT, is not connected to other balancing authorities within the United States. They're kind of isolated. So here, the little yellow dots are the balancing authorities and the blue ones represent watersheds. So ERCOT, the little yellow dot down here, is connected to the Trinity watershed because it has a hydropower facility in that watershed. And now, if you see that same Trinity watershed, it's also connected to MISO, which is another balancing authority. So even though those two balancing authorities aren't connected via electricity exchange, they could experience some of the same impacts on their hydropower facilities. And so this could incentivize sort of some like planning activities or other coordination, even though they're not connected through the infrastructure that we built. So this work has a lot to go. We have some preliminary results. We're trying to assess what will happen in each of the watersheds in terms of their stream flow in the future. So this is an example of some preliminary work. The watersheds here that are in orange are going to have larger interannual variability, meaning that the stream flow is going to change way more from year to year in the future. And the purple watersheds are going to have less interannual variability, so the stream flow will change less. So this will really like complicate planning, and this is something that could cascade through the system, and we're analyzing those impacts. So just to sum up, if there's like two key takeaways that I could leave you with, the first is that a changing climate is really going to have complex impacts on our energy infrastructure. There are lots of other smart folks working on this, but I think it's a huge problem. And because our energy infrastructure is so interconnected, this is really an interesting problem and could have real impacts on people and sort of the way that they get their electricity in the day-to-day. And I just also want to emphasize that I think it's really important that we create a resilient infrastructure for everyone, since this is really how we meet our day-to-day needs. And on the bottom, I have my acknowledgement of my advisor and my funding, and I will pass it off to the next presenter.
I'm not really sure how these usually work. Are we supposed to like allow people to ask questions?
We usually do questions at the very end so that
Okay.
everyone has a chance to go through the presentation.
Okay, great. Hopefully I am sharing the correct screen. Are you all okay, good. Hi, everyone. So my name is Gabby Salai. I am currently in the mechanical engineering program here at Penn State as a grad student, but my lab is in a really unique position because we actually do engineering education research. So the goal of engineering education is to have a positive impact on the educational experiences of all the students that are interested in engineering, regardless of their academic levels. So engineering education is pretty broad. You have people working on K-12 education, undergraduate engineering experiences, and you have people working on graduate student experiences. So my lab here at Penn State specifically focuses on student experiences at the graduate level. And some of the work that we are currently doing is trying to understand engineering graduate students' experiences when they are considering attrition. So attrition is defined as early departure from your program. So if you came in as a PhD student and you decided to leave with your master's degree instead of your PhD, that would be considered attrition or early departure. So today I'm going to be focusing on a specific part of research that I have been working on within my lab and within this broader context of graduate student experiences regarding attrition. So today we're going to be talking about how engineering graduate students cope with some of the prominent stressors in graduate school, and we're going to be looking at the mental health stress more specifically. So right now, there is a mental health crisis in graduate school that is being worsened by the chronic stress that students are experiencing while they're in school. So up to 2/3 of graduate students report high levels of stress, and graduate students are more than 6 times more likely to struggle with depression and anxiety than the general population. So though coping is considered part of like the common speech that we use when we talk about stress, it actually originates as a complex psychological construct that is based in psychological theory. And for engineering education research, it's really important for us to ground our work in theoretical constructs. So coping is colloquial now, and we talk about it all the time, but it comes from psychology, and it was like this big theory in the 60s. So we're asking, how are engineering graduate students coping landscapes? How are engineering graduate students coping landscapes when they're dealing with particular graduate school stressors being formed, basically? So to do our work, we recruited 42 participants through a nationwide survey, and we distributed this survey to the top 50 PhD granting universities all across the country. And we used something called maximum variation sampling for our recruitment process. And what this did was basically we recruited for diversity of gender, of amount of time in graduate school, of race and ethnicity, and experiences. And the purpose of using this was so that we could get a wide range of people with different experiences with regard to feeling like they want to leave their program early. After we recruited people, we then conducted semi-structured interviews with them, where we asked them things about their experiences while they've been in grad school. So semi-structured interviews are basically where we had some sort of interview protocol with questions that we were going to ask our participants, but we allowed for follow-up questions and for participants to kind of share what they felt was important about their experiences. So after we recruited and did our interviews, we analyzed our data in 2 phases. So the first phase was trying to understand all the different coping mechanisms that people use while to talk about and describe their experiences in graduate school. And so to do this, we used a modified version of an existing coping inventory with lots of different mechanisms in it. And we added a couple of extra mechanisms that were based specifically for graduate students in engineering. In the end, we had 16 coping mechanisms, which you can see here on the left. And then for the second phase of our research study, we actually mapped all of these coping mechanisms to 6 common stressors that our participants experienced. And these stressors were, some of them are based in literature. So we know that graduate students often talk about difficulties with their advisor relationship, or with their research and relationships with their lab mates, or with different situations with their department, including milestones that they have to complete to graduate with their degree. But also we had some stressors come out during our interview phase, where one of the stressors was people questioning. So because our research is about early departure, if you are considering leaving, that is, you're in the process of questioning, and this causes a lot of stress for students who are in this process. We also had a stressor of negative mental health stressor, which was basically people who were dealing with things like anxiety, depression, and PTSD because of graduate school. And then this last one is systemic stressors, which are basically dealing with issues of racism, sexism, ageism, and other sort of isms per se. For the purposes of this presentation, though, I'm going to be focusing on the negative mental health stressor that some of our participants experienced. So, participants who experienced this stressor used a variety of combinations of mechanisms to manage this stress. And this is what we call a coping landscape. So it just shows that, yes, some of our participants are using each of these coping mechanisms individually, independently, as we see it in the first column, but they also will use layered coping mechanisms to kind of deal with this stress. So the darker shading represents a higher frequency of participants who use these combinations of mechanisms. So active coping, which is when a student makes a deliberate effort to manage their stress head on, was consistently used to deal with stress, regardless of the stressor. And it was especially used to deal with negative mental health stress. Now, this closely aligns with the problem-solving skills that engineering students and the engineering discipline as a whole values and integrates into the engineering curriculum. So we were not surprised to see that it was one of the main coping mechanisms that was used to manage stress, and it was used often with other coping mechanisms in layered forms. And this kind of we weren't surprised to see this because we think that our participants are kind of applying the skills that they're learning to handle engineering problems to try and handle problems in their personal lives as well. So this study is actually the first study to show any overlapping nature of coping mechanisms and how these coping mechanisms kind of relate to different stressors that engineering graduate students experience. And while students are not always successful in managing their stress, they are constantly trying to improve their overall experiences to decrease this chronic stress. And basically, what we saw from our participants is that they are really trying to have agency over their lives and their experiences while they're in graduate school, even if they are not handling things in a way that some people would think is the proper way. Thank you.
Okay, so since we're doing questions at the end, I guess I will go ahead and jump in. I need to share my screen. First and foremost. Okay, can you all see my PowerPoint? Yes, awesome. Is the box with the camera thingy in front of the PowerPoint?
What?
How do I change it?
We can see your like presentation.
Is the box blocking it or is it fine?
No, it's fine.
Okay, cool. Alrighty. Then I'm gonna go ahead and get started. So we talked about environmental health a little bit with Lauren, and we talked about mental health a little bit with Gabby. So now we're going to talk more about physical health, but not physical health from the perspective of the patient, physical health from the perspective of the doctor and how well the doctor is trained to treat the patient. So my name is Sarola Maris. I'm a second-year PhD student in the Bright Lab under the advising of Dr. Scarlett Miller. So I'm industrial engineering, but I focus specifically on human factors and human-centered design. And even more specifically, I focus on medical human factors and designing training devices for medical personnel. So today I'm going to talk really just about training devices for doctors and get into a little bit of the history of that. So I just want to start by saying that most people in this room have probably been privileged enough to have been to a doctor at some point or another. Not everybody has that privilege. But everybody who has, I'm sure that you walk into the doctor, you get your treatment and you leave, and you don't really think a lot about how your doctor is trained. And so the more complex the medical procedure gets, the more complex the training and the more robust the training needs to be, because these doctors really need to be able to perform these procedures before they're actually going and performing them alone on patients. So I just want to point out to begin that there are three common components that tend to be on the path to medical school and becoming a doctor. It looks different for everybody. Some people take time off between these things. Some people don't. Like, it's very much not a linear path. But the three components that most people have in common who are doctors is they did some type of undergraduate education, they went to medical school, and then they had to go through a residency program. So my research focuses on training at the residency level. While there is training in both the pre-med and the medical school level, depending on where you go, the residency level is when you are actually an MD, you have the title, you are now a doctor, and you can now be trusted to start learning enough to do things on patients alone. But even at the residency level, especially in your first year, you're still learning so much. And so there are a lot of different ways that these doctors are trained to learn. And so one of the most common ways that medical procedures are taught at the residency level, and I believe also at the medical school level, but definitely at the residency level, is through mannequin trainers. And mannequin trainers are really beneficial because they can be either full body or partial body. So you can have just like a torso, you can have just a neck up, depending on what you're trying to train. And they're really beneficial because it gives doctors the ability to practice the mechanical skills that go into some of these complex medical procedures without actually having to perform on a patient, because it can be really dangerous. When people are learning, naturally they make mistakes. And so by having mannequin trainers, it creates more of a low stress environment for everybody involved, including the person who's being trained and the person who's training them. So like I mentioned, mannequin trainers are a really good low-risk way for doctors to practice mechanical skills. And so you can see in this video, this is the procedure that I work on. It's called Centromenas Catheterization. This is a half body or torso mannequin, but it belongs to Hershey Medical Center. And so this person is practicing inserting a needle into the neck of the mannequin. And so the idea is that in this procedure, it would be really easy, not easy because I don't want to scare anybody, but a lot of your anatomy in your body is overlapping. And if you don't know what you're doing, you can puncture the wrong thing. And that can be really, really dangerous. And so the idea behind the mannequin trainer is that if you're going to make the mistake, you do it on a mannequin and not on a person. So Centromenas Catheterization was what you just saw in that video. It is a medical procedure that is most often done when patients are in critical condition. So maybe in the ICU or about to have some kind of emergency surgery, and they need to get medication to their heart really quickly. So if you look at this image, you can see that little black line with the kind of the gray silver thing sticking out of it, that is a catheter. So it's not a catheter like a urinary catheter that most people think of. It is a catheter for medication delivery. And there are three main points that this catheter can get inserted. It has to go into a major vein. And so there are three, there's two in the neck, one in the internal jugular vein, one in the subclavian vein, and then one in the leg, which is in the femoral vein. And for the two that are in the neck specifically, the tip of that catheter, and I know less about femoral because we focus on the neck anatomy in my lab, but the tip of that catheter, as you can see in this image, that little black line, it goes directly into the heart. Like not all the way in, but it goes right to that edge of your heart. And so if somebody is not trained in how to do this correctly, it can cause a lot of complications that are both mechanical complications and then complications down the line that can lead to infection. So this is a really important medical procedure to make sure that people understand before they go and they do it on patients. And so one of the problems, while mannequin trainers are really, really useful because they're low risk, one of the problems, or some of the problems with them, is that they lack durability. So when, as you saw in that video, that person is using an actual needle and sticking it into the mannequin is made of a type of silicone rubber. That rubber is going to show track marks of the needle, which means that it's only going to be good for so long. If you go second, the track marks of the person who did it before you are still there. So it makes it a little bit easier for people to just copy what the other people did and not learn because the material is not really durable. Additionally, patient anatomical variability is a really huge one because not everybody has, while everybody tends to have the same anatomy in general, like of what is in your body, it's not going to be laid out the same. So we have an internal jugular vein where somebody has to insert a catheter, but the carotid artery is right next to that vein. And if you're going to insert something or you're going to puncture the carotid artery, arteries are really bad. They bleed and they pulse. So that's why it's really important, because some people, while the standard is some people have their artery on one side and their vein on the other, it can be flipped in some people. So you need to understand the anatomy really well, and you need to be able to change the sizes because it's also the size of somebody's artery or the depth of it. If you're very thin, if you carry more weight, the depth of the skin where those vessels are laying are going to be different. So when you have a mannequin trainer, again, when this is manufactured, you pick one anatomy and that's the anatomy that you manufacture into the mannequin. You can't change that. And then additionally, mannequin trainers, like you saw in that video, and like you can see here, this is the same idea. They only really focus on the needle insertion skill. You can't insert a full catheter into this mannequin because you can poke it with the needle and get the needle into the vein, which is the first step of Centromenas Catheterization or CVC. But you can't really dilate that rubber, and you also can't really slit it with a scalpel like you would for the skin to actually get the catheter in there, because it is not made of a material that allows that to happen. So it really is only focusing, while the needle insertion, because that's where you can puncture the carotid artery, it tends to be the most important step. It is not the only important step. And so that's one place where mannequins are really lacking. So there are some things that have already been done to try to combat some of these issues. And so this was something that has been worked on long before I got to Penn State. This is in 2016. People in my lab before me developed something called the Dynamic Haptic Robotics Trainer, or the DHRT, which was developed in order to try to fix some of these issues that exist with mannequin trainers. So one of the ways that it does that is that it uses a haptic simulator, a robotic haptic simulator, and a actual ultrasound screen with a simulated ultrasound and an actual probe. And so we can change both the anatomy and the layout and the feel of how it feels going to the neck. So while it doesn't look like a mannequin, we can argue that the fidelity might be lower visually. The actual mechanical fidelity of what you're doing is higher than with a mannequin because we're giving more anatomies. And so what we've done, or what they did in order to develop this, is they went into a lab at Hershey Medical Center and they got cadavers, and a lot of cadavers of different sizes. And for anyone who doesn't know, a cadaver is just a recently deceased or deceased but preserved body. And so what they did is they used these different force gauges and got force profiles of the neck for people of a bunch of different sizes. And then they took those force profiles and they programmed them into the robot. And that way, as you can see in these three pictures, one of those vessels is your carotid artery and one of them is your internal jugular vein. In the simulation, the artery pulses like it would in real life, and the vein is compressible like it is in real life. And then we can also see that the sizes are variable and the locations of them change. And so what would also change as the size and location change is the feeling that you get on the robot. So that robot would be putting haptics back against your hand when you're inserting it. So while this is really useful, it is still only focusing on the needle insertion step. And so what my research is optimizing what they've already designed as well as adding to it. So we're working on a new version of the system, which we're calling the DHRT Plus, which is basically just the addition of additional modules to the original system to actually train their procedure from start to finish. So right now, all that HRT does really is the first insertion step. What you see in that image is all it is. It has a probe for ultrasound scanning, and it has the needle, a blunted needle with haptic force that comes back on it. So what we're doing now is we're implementing the actual use of the full equipment tray. So the needle insertion is the first step. There's about, I believe, if I remember the number off the top of my head correctly, there's 12 more steps that come after and 5 different major tools that you need to learn how to use. So what we've developed now is the system that uses those tools along with a false vein channel to actually take the person all the way through the procedure. And so just to get a little closer on this, there are more steps that are important. And so that's really what I'm trying to emphasize. And so for this type of research, the way that we make sure that what we're doing works is we talk to a lot of doctors. So Gabby mentioned semi-structured interviews in her presentation. We did a very similar thing with doctors at Hershey Medical Center and Cedars-Sinai Medical Center in Los Angeles. And we took them through usability testing with all of the different usability. We gave them a demonstration of, we did this in 3 rounds. So we were making updates to our prototypes between the rounds. And then we went through semi-structured interviews and we gave them a survey about how they felt about our simulator. And based on that survey, pretty much everybody that we interviewed, and especially by the end when we had the final version of our prototype, said that they thought that this would be an improvement over current methods of training and that they would encourage their residents to train on this when it was available. So then once we got that feedback from the doctors, we actually took a prototype version of this, and that was the most functional. And we actually took it to a training and we trained doctors with it last summer. So we went to their residency boot camp. These were all the new people who just graduated medical school and were starting their journey in residency. And we took them and had them use our training. And then they went through proficiency testing. And then what we did is we compared their first time pass, like their chance of passing proficiency testing in their first time, and compared that to somebody who was not trained on this system, and actually found that our new system decreased your chance of failing on your first try. So that was actually really positive, and so that will help us move forward in the future. And so this is one of the ways that we make sure what we're doing is working, is we actually like bring it and we do human subjects testing. We train people on our system, and then we compare their performance to people who weren't trained on our system to make sure that we're actually seeing the learning gains that we expect. So it was implemented last summer. We're working on getting ready to implement it again this summer. This is what we looked like. This is what it looked like last summer in the training. So we had our false vein channel and our screen where they would actually go through the procedure, and we had an EKG monitor, and then they have all their tools on the side so they could actually go through the entire procedure with the false vein channel. We have an even better version of this now that I can't picture because it hasn't been tested yet and it's very private, but we have a new version of the system that we're going to be giving out. We're continuously making improvements and making sure that people are actually learning what we think we're learning so that we can make this procedure better for everyone. So that is all I have. Thank you so much.
Thank you guys. These were all really interesting talks. I want to open it up for questions from the audience. But in the meantime, I have a couple questions. My first one is for Gabby. So it seems like a lot of your research involves identifying grad student stressors and how students cope with their stressors. And I'm curious if you guys do work in identifying healthy ways of coping to help alleviate these issues.
Yeah, so that is future work for us. Right now, like I had mentioned before, there is actually like no literature in the engineering realm of like how graduate students are even coping with things. And so there is literature in psychology looking at healthy and unhealthy coping mechanisms that we would like to apply into to the types of coping mechanisms that we've already seen that our students use more often, but we just haven't done that yet. That is part of future work. And one of the things that we actually recommend in some of our work is that graduate programs, like in their first year seminars, have discussions about healthy and unhealthy coping mechanisms for students as they're going to start their graduate journey.
And I guess a follow-up to that. So it seems like a lot of this is focused on, the ways graduate students cope and like the issues that they're facing. But it seems like a lot of the stressors come from the graduate program itself. So for example, I know a huge stressor for a lot of people is their relationship with their advisor. And I know you're working with STEM education. I wonder if there's any future work in mind about educating PIs to be better managers, because they do all this training in STEM, but never any training on how to manage a group.
Absolutely. I completely agree with you. I think that there are people out there who are suggesting this. I think that one of the most important things is for advisors to learn how to mentor students as well, because that is not part of their training. Unfortunately, these tend to be systemic problems, where it's just this idea of like the advisor thinks I suffered when I went to graduate school, so you have to suffer too. And it's about dismantling kind of those systemic ways of thinking. I personally would like to do those things. It's just very difficult as individuals to dismantle those systemic systems. So I think that the first step is kind of getting this stuff out there so that people realize that there are problems. And now like trying to figure out what are some of the ways to do this. So I think future work would engineering education is really big on studying interventions. So future work might include creating some sort of program for faculty to learn how to mentor, and then seeing how that program actually works out within whatever discipline that it's implemented in.
All right, thank you.
Yeah.
I saw a question in the chat. This is also for Gabby. It says, if you could redesign graduate school with coping in mind, how would you do so? It's kind of a big question.
It is a big question. Thanks, Adam. Okay, so I think that the first thing I would do is try to reduce the stress that like students are feeling. Like I know that that's really difficult. There are certain things you have to do to be able to get a PhD. And like people always talk about a PhD has to be inherently more stressful because like not everybody goes for one. But I also don't necessarily agree with that. I think that one of the biggest things that I would do is I would really advocate and be an example of trying to establish healthy boundaries between my work and my life, because I think that that becomes a really huge part of like reducing some of the stress that people experience. So I think that the other thing that I would do is emphasize open communication between advisors and students, but also between students with each other so that they can talk to each other about what they're experiencing. Because a lot of what we saw in our research was that students felt like they were alone in the things that they were going through. But the reality was that, you know, all these people who were completely unconnected to each other and all over the country were feeling very similar things to each other and having very similar experiences to each other. So just for students to be able to have these conversations with each other, to know that there are other people around them that feel that way too, I think is a really valuable coping mechanism as well. I don't know if that answers your question, Adam, but yeah.
I see a question for Lauren. What role do you think ethics plays in engineering, perhaps especially in the trends we see of climate change?
Oh, I love this question, but it's also really hard. So we talk about a lot in my lab about sort of the dimensions of ethics in engineering that we don't normally learn about. So for example, like in our first year training in civil engineering, you learn about sort of like conflict, professional like conflict and sort of incentives, or sort of like you come to a construction site and you see that something is not done properly, and or there's environmental contamination, and what do you do and who do you report to, blah, blah, blah. But there are all of these other ethical dimensions that are involved in engineering every single day that we don't ever get training on. So for example, we think about this a lot like in modeling. So there are a lot of what we call like epistemic and ethical values and choices that you make when you're modeling. So for example, you could make choices about sort of the performance of the model based on what you think is a good metric. And that's like an example of an epistemic value. Or there are other like very subtle ethical values that you sort of like embed in your everyday engineering practice. And so in related to climate change, some of the like conflicts that I think about are sort of what we determine or what we decide are like okay thresholds for change, sort of what impacts we decide to simulate. Even, there are folks that I've heard talk about that we are making an ethical decision when we choose to use models that simulate 1.5 degrees of warming, 2 degrees of warming, or 2.5 degrees of warming, that we're implying that these are sort of our suitable range of scenarios. And there are, folks who will experience dire impacts at 1.5 and below degrees of warming. So there are all these like small choices related to ethics that are sort of embedded in our work that we do every day. And it's not even just, engineering. This is embedded in a lot of different science. We make a lot of like very small choices that could have ethical impacts. And I think rather than, them being the right choices, I think transparency is key. And so especially with related to climate research too, I think being very transparent about the choices that we make is really important to sort of understand the context of the situation and who might be impacted, and sort of really put our results into appropriate context.
Great, thank you. I think there's one more question for you. Based on your presentation, has there been any pushes for more deep sea hydropower to capture currents that may be more sustained?
Oh my gosh, this is a great question, but one that I don't know very much about like at all. So there are all of these people who are like wave energy enthusiasts. And I like ran into them at a conference, and they're great people, but this is like outside of the scope of my domain. So there's definitely like more research in this area, which is very exciting, but it's not like a space that I know very well. The US actually like isn't developing hydropower, right? Like we've sort of developed all we can. And so like the research in that space is really interesting. We're mostly like retrofitting, upgrading facilities, and also just trying to put like very small scale hydropower on existing like rivers and conduits and all of these things. So I don't know I don't know the space very well, but it's very exciting.
Yeah, that's fine. Thank you. Let's see if there's here. This is for Harula. What's it like working with users who are professionals in a different field? Do you have any tips?
Yeah, that's a really good question. And basically everything we do is very interdisciplinary because, I am an industrial engineer who designs interfaces, working with a mechanical engineer who does all the haptic robotic stuff. And then we actually use our stuff on doctors. So we have a lot of people who have their hands in a lot of different things. One of the hardest parts of working with doctors is that, like medical doctors, is their schedules, especially because so much of our research, so I didn't mention this in my presentation, but a lot of the people who are doing these Centromenas catheters are surgeons. And surgeons are very difficult to schedule with because they, especially for emergency surgeries, they can get pulled in a lot. And so I think one of the things that has been the most beneficial for us is a little bit counterintuitive, but when it comes to like planning our studies, we wait until we get closer to them to actually schedule people because surgeon schedules are so volatile. So for example, we were supposed to be going down to Hershey this week, and we weren't going to reach out to any surgeons until we were supposed to be going down on Monday. It's gotten rescheduled, but we are on Wednesday, but we weren't going to be reaching out to anybody until Monday because we know that if they put it in their calendar early, it's not going to happen. And we're also working with two different types of doctors, which we call experts and novices. So expert doctors are people who have done more than 50 of this procedure, whereas novices are people who've done less. The experts are the ones who are very, very difficult to schedule with because they're people who are very high up, whereas the novices are usually medical residents who are just doing whatever they're told. And so I think keeping open communication and being really flexible are two of the things that help us the most in working with this group of people.
There's a question in the Q&A. Also for Harula says, do you think using VR to train doctors can achieve similar results to the improved ex vivo testing you're looking into right now?
Yeah, I think that's a really, really good question, very timely, because we're actually working on adding a VR component to this research or to this training. I don't think right now with the VR is really good and it can do a lot of things, but it's still expensive and kind of limited to actually get the haptic VR stuff. And it's not, as far as I know, I don't know a ton about it, but I don't believe, and you can correct me if I'm wrong, Freya, but I don't think that the haptics are to the point yet where in virtual reality, they would work as well as we would want. So right now, what we're using VR for is we're adding like a pre-training because people have very limited time too. So even when they were back doing the mannequin trainers before they started implementing our system, it was really difficult to get people the best amount of time that we could. So the best amount of time that would help them with the procedure. So what we did is what we're doing now actually is we developed a desktop VR so that we don't actually have to be there with the headset, that people could do from home, that would walk them through the procedure and actually see the medical kit, be able to mess around with it in VR, drag it to the person and do all of that stuff. Then they take an online curriculum. Well, actually, they take an online curriculum first where they have to watch 8 videos and they learn all the intricacies of the procedure. Then they do the virtual reality training and then they actually touch our system and then they do proficiency testing. And so our goal this summer is to see if now we have these 3 things, 2 they do at home, 1 they do in person, so that we can get them through the training since time is a very limiting factor. And we're going to see if adding the virtual reality makes any positive difference. And that is a good question.
Very cool. I think we have time for this one last question. It's a follow-up from earlier. How easy is it to work with the robot? How do you make sure the robot is working as intended since it seems so critical to your studies?
Yeah, so I don't work that much with the robot, unfortunately. I know how to turn it on and I know how to use it for the simulator, and I know some of the basic programming behind it, but that is really, like I said, it's a very interdisciplinary project. So most of what I do is the human interfacing. So if I don't like something about how the robot feels, I tell the mechanical engineer, and then that person is the one who actually goes and like fixes the things in the robot. It is very tricky to answer your question because sometimes it just breaks and we don't know why. Or like we have a robot that the arm can like flip directions based on if we have a left-handed user or right-handed user, because they would switch which hand they're doing things in. And there have been times where it's maybe not very intuitive, which human studies, this is something that we're trying to make sure people understand better. And people will go up to the robot and try to flip it and they broke the arm. And those robots are thousands of dollars. So I would say the hardest part about working with the robot is just when the robot doesn't work.
All right, thank you guys so much. I think we're done with questions, but I really appreciated all of your talks. I think you broke it down for a general audience really well. I will definitely post this online, and yeah, thank you guys again so much.
Thank you, Angela.
Thank you.
Thank you.
Fun.
Yes, thank you.
All
for
right, have
having
a good
me.
rest of your evening.
Thanks,
Thank
you too.
you. You too.